Hi everyone, welcome to the ATAR Notes January 2024 lecture series. This is the Chemistry Unit 3 and 4 lecture. So a little bit about ATAR Notes. ATAR Notes provides a bunch of resources to help you get through your QCE. So we've got hundreds of downloadable study notes, lectures such as these ones where you can learn from past students, an online Q&A discussion board to ask any burning questions that you have, videos to help with engaging online revision, newsletters to help you stay in the loop with what's happening, an ATAR calculator to check if you're on track to achieve your goal ATAR, articles which contain heaps of great study strategies and tips, and heaps more, so make sure to check out the website. There's also thousands of paid study resources in our new ATAR Notes Plus. And so ATAR Notes Plus has the flashcards, the complete course notes, and a new AI answer bot. And these are all great resources that will really help you to achieve your goals for your Year 12 study. So a little bit about me. So my name is Amelia and I graduated from Matthew Flinders in 2021. I'm currently studying medicine in UNSW in Port Macquarie. And so if anyone has any questions today about the content that we're going to cover or my degree or anything like that, just feel free to ask. So here's a bit of an overview of what we're going to be going through today. So we'll start off with looking at what redox reactions are, and we'll put those into a bit of context and provide a few examples and just talk through how they apply to our day-to-day lives and sort of just that general importance of redox reactions and their vast applications in day-to-day life. We'll then look at oxidation states, which are the various different states in which elements or atoms can exist in such that they can participate in these redox reactions. Then we'll look further into what are redox reactions, what's the different concepts of oxidation and reduction are, and how these two concepts work together in order to enable this reaction to occur. Then we'll look into predicting and identifying redox reactions. So that's looking at two different particular species of atom and considering which one's going to oxidize, which one's going to reduce in that particular given circumstance. And those will vary depending on what molecules are reacting with other molecules. Then we'll look into balancing redox reactions. And so this is similar to what you may have done in the past with balancing a normal chemical reaction. However, this is then looking into balancing a redox reaction, which is a little bit different in that you not only need to balance the compounds and their elements, but you also need to be able to balance the charges, and those charges in that they'll be changing from the left side to the right side of the reaction, and so balancing out those charges for both sides of the reaction. And so that will be considering that under standard conditions, which is just going to be at a basic, just your standard pH of around 7. Then we'll consider the acidic conditions, and there's also some basic conditions which are a little bit less of a concern. You don't really need to worry about those too much. And we'll look through some examples of those, some step-by-step examples, just to completely solidify those concepts. And then finally, we'll finish off with a few study tips. So that's just a few different ways to help you stay on top of your study and to really optimize your grades for chemistry and other subjects as well throughout grade 12. So far in topic 1 of unit 3, which I would assume most people have already started towards the end of last year, you would have looked at equilibrium, acids and bases, pH, and then indicators and titration. So I'm assuming so far that everyone's going to have a generally okay understanding of those concepts. Then in topic 2, we're looking at a concept which is going to build on these a bit, and use some of these concepts of acids and bases and equilibrium, pH, not so much indicators and titration, but a little bit. And we're going to look at those concepts and build on top of them. And so hence you're going to need, in order to understand the rest of year 12, you do need to have quite a solid foundation of the beginning topics in order to then understand the following on topics. So it's making sure that I'm sort of just reiterating that you need to make sure to stay on top of what you're learning, because you can't forget the previous stuff that you've learned, otherwise the next things which you learn aren't going to make much sense. So we'll start off with oxidation states, and we'll look into redox reactions. And so this is just a bit of an overview of what our redox reactions are. So essentially, redox is a type of reaction. So you can consider, like, you've got your addition reactions, your decomposition reactions, your combustion reactions, your single displacement, double displacement. You've got all those types of reactions. Redox is just another one of those types of reactions. And so essentially where the word redox comes from is that it's reduction, oxidation. So first 3 letters of reduction, first 2 letters of oxidation. And so essentially what a redox reaction is it is a reaction which is going to involve a transfer of electrons between 2 different species. So that being like 2 different molecules, 2 different elements, 2 different atoms. They have a supposed charge, and they are sharing electrons, transferring electrons between them in order to change that charge. And so hence we've got the reduction, which is a gain of electrons, and the oxidation, which is a loss of electrons. And so these redox reactions, they're very important. They're some of the most important reactions which we have, and they're occurring everywhere all the time, consistently occurring in your body. So, for example, our bodies use redox reactions in cellular respiration, so converting sugar and oxygen into energy, water, and carbon dioxide. Another example we have is that batteries, they rely on a redox reaction, and we'll go into that in a bit more depth later on, because that's quite an important concept in this topic, particularly when we think about things like galvanic cells and electrolytic cells, which are a type of battery. So oxidation states, or we can also call them oxidation numbers, are this number which we use, and we use it to keep track of how electrons are being shared within a molecule or atom. And it also helps us to then understand how the electrons are being transferred from a molecule or an atom to another molecule or atom. And so essentially this number represents the number of electrons that can either be gained, lost, or shared within a molecule. And there's a few rules which we need to cover in order to be able to then assign these oxidation states. So we'll go on to talk about those in a minute, and those are really important that you follow them in order, because they have quite a specific structure and are ordered in levels of their importance and priority. So you need to make sure that they're followed in order, and they are quite important to follow them in that order. And then also just throughout the slides, just to let you know, we're going to abbreviate oxidation state or oxidation number to either OS or ON, just to make that a little bit easier, just because to save writing the whole word. So just to clear that up so you don't get confused what that means. So these are our rules for the oxidation states. So rule number 1 states that any individual atom that is not combined with other elements is going to have an oxidation number of 0. So an example of that being, we've got oxygen, oxygen gas, which is O2. And so as long as that doesn't become combined with any other element, O2 will sorry, O2 will just become O2 with its oxidation number of 0. Similarly, if you just had magnesium and it was just like Mg, magnesium, it would also have its oxidation number being 0 because it's not combined with any other element. So you could also have something like ozone, which is O3, and as long as that's not combined with any other elements, it's just O3 because it's purely made of oxygen. O3 would then be considered to have an oxidation number of 0. Our second rule is that the sum of oxidation states of all of the atoms in a species will be equal to the net charge on that species. So there's a part A and a part B to this rule, and that's just because there's different ways which we can consider this for both a neutral species and for ions. So in a neutral species, the total sum of the oxidation state of all of the atoms is going to be 0. But that's the entire molecule will be 0. So, for example, if you have something like NaCl, sodium chloride, its entire because it doesn't have a charge on it, it's not an ion, it's going to have a sum of oxidation states of 0 in total. However, its individual atoms within that molecule are going to be charged. So its oxidation state is going to be 0, but that's because the sodium and the chloride are each going to have a value which then adds up to 0. So, for example, the sodium is going to be +1, and the chlorine is going to have an oxidation state of -1, hence giving -1 + 1 gives 0. And so hence then you have the total oxidation state for the entire molecule being 0. And so that's important when you get the questions which ask you, you have sodium chloride, what is the oxidation state of sodium? And then you would know that, oh, it's going to be +1. For part B of this rule, we consider then ions. And so we have to consider that the total sum of the oxidation state is going to be the charge of the ion. So, for example, the oxidation state of calcium 2+ is going to be +2. So you have Ca2+, and its oxidation state is +2. And so if we're then, that's just an individual ion in its own regard. so we don't need to consider anything else. We can just say that the oxidation state of the calcium in calcium 2 plus is 2 plus. However, if we're considering an ion which has multiple different atoms in it and multiple different elements, the total sum of the oxidation states of all of those are going to add up to the charge of that particular ion. So, for example, if we're looking at the chromate ion, which is CrO4 2 minus, the entire chromate ion is going to have an oxidation state of -2, which means that everything in that needs to add up to -2. And so this is where it gets a little bit tricky, because you do have to apply some of the rules which we haven't looked at yet. We'll look at those next up. But basically, I'll give you a little bit of a preview into what they are, just to explain the chromate ion. But basically, each oxygen atom is going to have a charge of -2, which means that if you have 4 of them, that's going to be -8. And so if you have -8 from all the oxygens, that means you're going to need to add them up to -2. And so the only thing you then have left is the chromium. And so the chromium, you need to have the appropriate value such that you can get from -8 to -2. So you need to determine what's the difference between -8 and -2. That means that when you add the oxygen ion charges and the chromium ion charges, they add together to get -2. So if you've got -8 for the oxygen, you're then going to have +6 for the chromium, because -8 plus 6 is going to give you -2. So rule number 3 is that in a compound, the oxidation state will be based on the group in the periodic table. So for example, our group 1 metals, which are like sodium, are going to be 1 plus. If we're considering chlorine, that's down the other end, and that's in our group 15, and that's going to be a -1, because it's just based on those general ion rules when you're making an ionic compound. So for example, that's how you know when you have NaCl, chlorine is going to be -1 and sodium is going to be +1, because it's just following that general rule 3, as well as then combining that with the rule 2, which we have here. Rule number 4 is sort of just like an example type one which they give, because it still fits into the category of rule 3, but it's just very specified in order to sort of provide more context, I suppose. And so the oxidation state of fluorine is -1 in a compound. So when you have a compound that has fluorine in it, each fluorine is going to have an oxidation state of -1. Rule number 5 is that the oxidation state of hydrogen in a compound is going to be +1. And so that differs from rule 3, because rule 3 tells us that group 1 metals like sodium are going to have a +1 charge. And so hydrogen is not a group 1 metal. It exists in a gaseous state, and so that's why that's quite clearly specified for rule 5, because although it fits in group 1, it's not considered a group 1 metal, so it's kind of given its own little thing. Yeah. Then rule 6 is that the oxidation state of oxygen is -2 when it's in a compound. And so obviously that's going to vary. If you've got something like O2, well obviously that's going to follow our first rule, which we have here, that the oxidation number is going to be 0, because remembering we follow the rules in their chronological order. But the oxidation state of oxygen is -2 in a compound. So for example, combining rule 5 and rule 6, if we were to have water, which is H2O, the oxidation states of hydrogen, each one is going to be +1. And so because there's 2 of them, 2 times 1 is going to give us 2. And then the oxidation state of oxygen is going to be -2. So 2 minus 2 gives us 0. And because water is not charged, we can say that that then gives us an entire oxidation state for the water molecule of 0. Rule number 7 is that in 2-element compounds with metals, group 15, so 5A elements are going to have the oxidation state of -3. Group 16 or 6A elements are going to have an oxidation state of -2, and group 17, 7A elements, will have an oxidation state of -1. And so with this, it seems like there is a lot of rules, but many of them have quite a lot of overlap in them. So rule 3 is quite closely tied in with rule 7. Rule 4 also ties in quite closely with rule 3, and you could almost consider rule 5 to tie in quite closely with rule 3 as well. The only difference being that hydrogen's not a group 1 metal, it's just a group 1 element. So if we're to just look at this here, just to kind of get an understanding with rule 7, we can see that we've got like our group 17, they're going to be the 1 minus charge. Then there's going to be like our 2 minus charge here, or -2 charge in group 16. Group 15 is going to be a -3 charge. This group here is quite variable, same with this one here, but typically this can be +4 or -4, but that will vary quite a bit. This one would be the +3, but that also varies quite a bit. This one here is +2, and this group here, group 1, is +1, as we spoke about before. And so we can see here these are our group 1 metals, which are fitting in with group 3, and then we've got hydrogen up the top here in group 1. Obviously not a metal, but still kind of following that general rule. So we're just going to go through a few examples of these. So our first one here is quite simple, and so the first thing we're going to do is look at rule number 1, because when we go back to rule number 1 tells us that any individual atom not combined with other elements will have an oxidation number of 0. And remembering our example was O2, that's purely made up of oxygen, no other elements in there. Despite it being 2 oxygen atoms, it's still only made up of oxygen. So our first example we've got is Cl2. It follows that same kind of general rule, and so we can say that any individual atom not combined with other elements has an oxidation number of 0. So we can see that this is going to apply here to this case because chlorine isn't bound to any element other than itself. So each chlorine atom is going to have a charge of 0, and the overall Cl2 is going to have a charge of 0. Our next one which we have is NaH, sodium hydride, and so right off the bat in this case, we know that rule number 1, we don't need that because we've got 2 different types of elements in this one particular compound, and we can see that sodium is bound to a hydrogen, hence there's 2 different elements. So next we can look at rule 2, and so rule 2 tells us that the sum of the oxidation states of all of the atoms in a species is going to be equal to the net charge of that species. And so this rule does apply here, and this rule will basically apply all of the time. And so we know that the sum of the oxidation states for sodium and hydrogen is going to be equal to 0 because the compound is neutral. And so we might be inclined to jump ahead to rule number 5, where hydrogen has its oxidation state of +1. However, we do need to consider the rules in their proper order. So we've gone to rule 2. Next, we need to consider our rules in their specific order. So we remember that sodium actually has a charge of +1, and so hence hydrogen itself could not have a charge of +1 as well, because we know that the compound itself is going to be neutral and have a charge of 0. So if we had +1 and +1, we'd end up with an overall charge for sodium hydride of +2, and that wouldn't be correct in this circumstance. So we need to actually change the one which hydrogen is in this particular example. And so this is one where there is hydrogen is going to differ from that rule, and that's because the sodium rule, where we're looking at the group 1 metals, is rule number 3, whereas our rule with hydrogen is rule number 5. And we remember that we do the rules in their specific order. So we would say that sodium is going to be +1, and so if sodium is +1 and we want the entire molecule to equal to 0 for its charge because the compound is neutral, we know that the sum of the oxidation states for sodium and hydrogen is going to have to add up to 0. So if we have +1, we have to do +1 with what is going to give us 0. So hydrogen is going to have to be -1. So we'd have +1 for the sodium and -1 for the hydrogen as the oxidation states. So we can say that the oxidation state for the entire molecule is going to be 0, but the oxidation state for sodium will be +1, and the oxidation state for hydrogen will be -1. Our next example that we've got is hydrogen carbonate, and so once again we're going to skip rule 1 straight away because we have a compound which has multiple different elements in it. So we immediately have crossed off rule number 1 there because it can't fit into that because we've got various different elements. So next up we've got rule number 2. And so with rule number 2, we can see that there is no charge overall, and so the sum of the oxidation states needs to be equal to 0. And so like anything which doesn't have a charge on it, the entire molecule is going to have an oxidation state of 0. And then in this case, we know that rule number 3 is not really going to apply because we don't have those kind of set out group 1 metals in there, or group 17 elements, so we can't apply that. And this is because it's mostly composed of hydrogen, carbon, and oxygen. So rule number 3 is typically more useful for other elements. And so in this case, we need to go on to our next rule, which is applicable, and that would be our hydrogen rule. So our hydrogen rule is telling us that hydrogen, we go back to our rules, we can see that hydrogen is going to be +1 in a compound, and oxygen is going to be -2 in a compound. So we can skip forward and we can say, well, each hydrogen is going to have a charge of +1. So we've got 2 of them, so it's going to be 2 times +1. So that gives us a charge of 2. So each hydrogen has a charge of +1. But overall, because there's 2 of them, we need to say that we've got +2. We know from rule 6 that oxygen has a charge of -2. So we can say -2 +2, that evens us out to 0 already. And so there's no charge overall in this entire compound. So if we've already got to 0 and we haven't actually factored in the carbon yet, that means we need to say that the carbon actually has an oxidation state of 0. So when we're considering this, the carbon's not really participating in the oxidation if this compound were to participate in an oxidation reaction. We'll look into that a bit further in a moment. But essentially, we can say that this entire molecule has an oxidation state of 0. Each hydrogen atom has an oxidation state of +1. Each carbon atom has an oxidation state of 0. And each oxygen atom has an oxidation state of -2. And so if we add those all up, we have +1, +1, +0, -2, and that gives us 0 overall. Our next example is looking at KMnO4, so that's potassium manganate. And so rule 2 tells us that the sum of the oxidation state should be 0, and again that's because potassium manganate does not have a charge, and so overall its oxidation state will be 0. We can then use rule 3, which tells us that potassium has an oxidation state of +1, because rule 3 tells us that our group 1 metals, such as potassium, have an oxidation state of +1. Rules 4 and 5 aren't going to apply because we've got no fluorine and no hydrogen in this particular molecule. And then so we next go on to rule 6, and rule 6 is going to tell us that oxygen has an oxidation state of -2. The thing we then need to note here is that we've got +1 for potassium, and then we're going on to oxygen, and we've got 4 oxygens. And so each oxygen, we need to remember, is going to be minus 2. But we've got 4 of them, so we've got to do 4 times minus 2. And so that gives us minus 8. But we're wanting to figure out what the oxidation state of manganese is. So we need to add up what we've got so far. So if we've got minus 2 times 4, that's going to give us minus 8. But then we've got to do minus 8 plus 1 because of the potassium. So we do minus 8 plus 1, and that gives us minus 7. So if our oxidation state without the manganese is minus 7, and we want to get it to 0, that tells us that the oxidation number of manganese is going to be plus 7. So if we go through the oxidation states for the entire molecule, the oxidation state for the molecule as a whole, for the entire potassium manganate, is going to be 0. The oxidation state for potassium is going to be plus 1. The oxidation state for the manganese is plus 7. And the oxidation state for each individual oxygen atom is minus 2. However, we have 4 of them, so all up they'll be minus 8. But when we're saying the oxidation state for the oxygen, we're saying that each one is separately and individually, so it's minus 2 for oxygen. So now we're going to go into talking about a redox reaction and a bit of an overview into understanding these oxidation states a little bit better with the application of the oxidation and reduction, or our redox reactions. So basically, now that you understand the oxidation states, we can then apply these and cover our processes of oxidation and reduction. So there's quite a useful acronym which people use and you can use to remember these processes, so the processes of oxidation and reduction. And this acronym is called OIL-RIG. And so we say that oxidation is loss, reduction is gain. So oxidation being the loss of electrons and reduction being the gain of electrons. It's also good to remember that they sort of sound the opposite of the way they're meant to be. Because if you think about it, reduction seems like it should be a loss of electrons, but reduction is actually a gain of electrons. And you would think that oxidation is then going to be the gain of electrons, but it's actually the loss of electrons. And so this is basically these values, as I already mentioned, are referencing to the change of electrons which occur in a redox reaction. So basically, if a species is oxidized, it loses electrons, whilst if it is reduced, it's going to gain electrons. And then opposite to this is a change of oxidation states. So if a species is oxidized, its oxidation number is going to increase. So for example, you have something with a 2+ oxidation number and it becomes oxidized, it's lost electrons. If it's lost 1 electron, it will then become 3+, and that's because we remember that electrons have a negative charge. So if you're to take away an electron, that means you're taking away negative charge, giving the element a more positive charge. And so the species that is oxidized is called the reducing agent because it causes the other one to be reduced, whilst the species that is reduced is called the oxidizing agent because it's causing the other one to be oxidized. And the way in which it's causing the other one to either be oxidized or reduced by doing the opposite is because this is a sharing of electrons type process. So when the species is oxidized, it's losing electrons, but it doesn't just lose these electrons to nowhere, because you can't create or destroy the electrons. So it's losing these electrons by transferring them to the species which is being reduced, hence it being called the reducing agent, because it loses its electrons and donates them to the molecule which is going to then gain the electrons. And so the species that is then reduced, so the one gaining electrons, is essentially taking electrons from the one which is being oxidized, hence causing the one which is being oxidized to then be oxidized. So these reactions are dependent on each other. You can't have an oxidation without a reduction, and you can't have a reduction without an oxidation. They work hand in hand, because you need one in order for the other to occur. As I previously said, like, you can't lose electrons to nowhere. They have to be given to another species. Same with, you can't just gain electrons from anywhere. They have to actually be taken from somewhere else. So it's important to note that these, as I said before, these redox reactions are composed of two parts, so the reduced half and the oxidized half. So you can actually split, instead of writing it as one big reaction, you can actually split these reactions into the reduced half and the oxidized half. So there's no net change in the number of electrons in a redox reaction, which means that no electrons are gained from or lost to the environment. So basically, as I said before, like, in the entire reaction, there's actually not a net change in electrons. There's just a transference of electrons from one species to the other. So we can look at an example, and this example here uses zinc and hydrogen ions, and it shows us a transference of electrons, and it's also balanced to show how the ratios work, such that you can have something with different charges create the same charge. So essentially, we want to look at what is happening here in this reaction. So if we're taking note of this, we can see that the oxidation state of the hydrogen is going from +1 to 0, because remember, applying our rules say that anything with a charge is going to, its oxidation number is going to be the charge of that given ion. And then our other rule states that anything that's entirely made up of one type of element is going to have an oxidation number of 0. Hence, hydrogen gas, or H2, has its oxidation state of 0, whilst H+, our hydrogen ions, has its oxidation state of +1. And so we can see it's changing from +1 to 0, and then our oxidation state of zinc is changing from 0 to +2. And so we can see this is going to be 0 because it's entirely made up of one type of element, and so hence that's rule 1, it's going to be 0. And then obviously with our zinc here, it's got a charge of 2+, and that comes to part of rule 2, in that the charge of an ion, if the entire molecule is an ion, then that's going to be its oxidation state. And so that's the rule here, where we've got zinc 2+, its oxidation state is going to be 2+. And so then we need to look at, well, what's being oxidized and what's being reduced. And so this is where it can get a bit tricky, in that you need to pay a lot of attention to the detail and remember that what is being reduced is gaining electrons, and what is being oxidized is losing electrons. And you then also need to consider that what is gaining electrons will end up with a more negative value than it started with, and what is losing electrons will end up with more of a positive value than it started with. So, for example, we're then looking at zinc, and we can say, well, zinc is going from 0 to 2+, so it's becoming more positive. We know electrons are negatively charged, so if zinc is becoming more positive, it must be losing electrons. And so when we say what is a reaction where the species loses electrons, that's going to be our oxidation reaction. So we can say the oxidation state of zinc is going from 0 to 2+, so it's losing 2 electrons, and so it's being oxidized. And then we need to remember that what is being oxidized is going to act as a reducing agent. So we can say zinc is oxidized, and we can also say that zinc is the reducing agent. We can then look at hydrogen, and we can say that hydrogen is going from a 1+ charge to a charge of 0. So it's becoming more negative. It's going from 2+ with those 2 there, so 1+ per hydrogen, to 0. So where each hydrogen atom is going to be losing 1 electron. So when it's losing an electron, we remember that it's gaining 1 electron. It's going from +1 to 0. That's going to be a gain of 1 electron, because we're remembering that our electrons are negative. And so that means that it's being reduced. Hence, hydrogen is going to be reduced, and it's going to act as the oxidizing agent. So overall in this reaction, we've got zinc going from 0 to 2+, and it is being oxidized and hence acting as a reducing agent. And so it's giving away these 2 electrons and donating them to this hydrogen. So this hydrogen can be reduced and gain those 2 electrons, an electron per hydrogen atom, to then become H2 with its charge of 0. And so to look at this more clearly, we can also break it up into half reactions. So we can say that the zinc forms zinc 2+ plus 2 electrons, and you can do 2, and so that would be our half reaction for the oxidation of zinc, whilst we can also then do beneath that 2 electrons plus 2 hydrogen ions makes hydrogen gas, and that's showing our reduction reaction, which is showing the reduction of the hydrogen ions. So there's quite a number of different redox reactions which we need to consider. So we've got our combination reactions, our decomposition reactions, single replacement or single displacement reactions, double replacement or double displacement reactions, combustion reactions, and disproportionation reactions. So you've probably come across most of these, if not all, throughout your chemistry journey so far. And so I would say that you'll have a general understanding of what these are, but probably not in the context of redox. So we're going to go on and talk about what these different types of reactions are and how they work. So our combination reactions, these are the most simple type of reaction which we consider. They're quite basic and typically don't require an extensive amount of balancing. And essentially they're where two different elements are going to be combined to then form one chemical compound. And so we can consider the combination of hydrogen and oxygen. So for example, where we've got 2H2 plus O2, and that's going to make 2H2O. So if we're to consider how we look at this in a redox context, we could say that we know that each hydrogen atom is going to have a charge of 0 because it's H2, it's solely made up of hydrogen, and so hence, because it's only made up of hydrogen, each hydrogen atom is going to have a charge of 0. We can then look at oxygen, which is the exact same concept, because it's oxygen gas, it's entirely made up of oxygen atoms only, and so hence each oxygen atom is going to only have an oxidation number of 0, and the entire molecule will also have an oxidation number of 0. So we can say that this is 0, this is 0, and then when we get to the final reaction, we can see that following our rules that we have, so rule number 5 is going to tell us that hydrogen is going to have an oxidation number of +1 per hydrogen atom. So because we've got two of them, it's going to be 2 times +1, which gives us +2. And then we know based on rule 6 that oxygen is going to have its oxidation number of -2. So we've got +2 and -2, and that gives us 0 overall. And so when we consider that, that tells us that water has an oxidation number of 0, oxygen has its oxidation number of -2, and hydrogen has its oxidation number of +1 per atom. And we can say that this is redox because hydrogen is going from 0 to +1, so it's losing 1 electron per hydrogen atom, whilst oxygen is going from 0 to -2, so it's gaining a electron per hydrogen, 2 electrons per hydrogen, per oxygen atom. So essentially the oxygen is receiving electrons from the hydrogen atoms. So when the hydrogen loses those 4 electrons, because we've got 2 times 2 is going to give us 4, it's going to lose 4 electrons and give those 4 to the 2 oxygen atoms, because 2 times the oxygens, and then those 4 electrons which are lost from the hydrogen, resulting in the hydrogen being oxidized and the oxygen being reduced. And so if we consider that in terms of the oxidizing and reducing agents, we can say that hydrogen is the hydrogen is the reducing agent, and oxygen is the oxidizing agent. Our next one we can look at is the opposite of that, so that's our decomposition reactions. So a decomposition reaction occurs when a chemical compound breaks down into each of its constituent elements. So we can see here we've got AB makes A plus B. So essentially they've just been separated down into their constituent parts, and typically these are just the opposite of your combination reactions. So often you can have a combination reaction that is reversible and can reverse back down into this. So if we're to consider, for example, the decomposition of water, it's basically just the opposite of what we just looked at before. So we can say we start off with H2O, and so we've got 2 H2O, and so we know that the hydrogen is going to be a +1 charge per hydrogen atom, and the oxygen is a -2 charge per oxygen atom. And we know that once we get to the H2 here, that's got a charge of 0, because that's following rule 1. It's only made up of one element type. And same with our oxygen, that's only made up of one element type. So when we're looking at hydrogen, hydrogen is going from +1 to 0. So it's gaining an electron per hydrogen atom. Whereas our oxygen is going from -2 per oxygen atom to 0 per oxygen atom. So we can say that the hydrogen, in going from +1 to 0, is gaining 1 electron per hydrogen atom, whilst the oxygen going from 0 to going from -2 to 0 is losing 2 electrons per hydrogen atom. So because of that, we can say if hydrogen is gaining electrons, we can say that hydrogen is being reduced, whilst the oxygen is losing electrons, we can say the oxygen is being oxidized. And so if the hydrogen is being reduced, that means that it is the oxidizing agent, because when it loses its electrons, it's donating them to, so when it gains those electrons, it's being donated them by the oxygen. So the oxygen is losing 2 electrons and hence is being oxidized, and so hence it is the reducing agent. It's causing the hydrogen to be reduced. So essentially the oxygen will lose 2 electrons and enable the hydrogen to be reduced by donating those 2 electrons, and the hydrogen will have from the water will have lost electrons, will have gained those electrons in order to enable the oxygen to then actually donate those across. The next reaction we're going to look at is a single displacement reaction. So a single displacement reaction involves the replacement of one element with another element within those products. So we could consider if we have A plus BC, we do a swap over and we end up with AB plus C. So a really good example that we've got here is we've got Cl2, so that's chlorine gas, plus 2 NaBr, so 2 sodium bromides, and then we've had a single displacement reaction which has resulted in the formation of 2 sodium chloride, or NaCl, molecules and bromine gas, or Br2. And so we can say that this is a redox reaction because not only is this a single displacement reaction in which we can see that in this compound of NaBr we're swapping out chlorine for the bromine, but we've then also got that it's a redox reaction in that we can see the chlorine is starting off as a charge of 0 in total, so its oxidation number is going to be 0 based on rule number 1 because it's entirely made out of chlorine. Then we can see the sodium and the bromine. We can go on to our rule number 3, which tells us that sodium is going to have a +1 oxidation number because it is a group 1 metal, and we remember based on rule number 3, group 1 metals will have a oxidation number of +1. And then we've got bromine, and we know with bromine that fits into our rule number 7, which tells us that our group 17 elements are going to have a charge or an oxidation number of -1. So +1, -1, and yep, that's right, that gives us 0 in total, and this is an uncharged molecule, so that's correct. We can then see, so chlorine's going to go from 0, sodium is going to go from +1, and bromine is going to go from -1. We can then see in our next, in our products, that sodium, we've got sodium chloride. So following our rules again, we go to rule number 3, which tells us that sodium is going to have its charge of +1 because it's in group 1 of the periodic table and it's a group 1 metal. Then chlorine, going on to rule 7, we know that our group 17 elements are going to have a charge of -1. So we've got sodium is staying as +1, but chlorine is changing to -1. So chlorine is going from +1, 0 to -1. So chlorine goes from 0 to -1. So it's gaining 1 electron. Then we look at bromine, and bromine here is bromine gas. And so bromine gas is purely made up of just bromine. So we use rule number 1, which tells us that its oxidation number is going to be 0 for each bromine atom. So we can see that bromine is going from -1 to 0. So this is an interesting one in that the sodium is what we call a spectator ion. And so a spectator ion does not participate in the reaction as such. So it's there participating in the reaction itself, but not participating in the redox component of the reaction. So it's not actually changing its oxidation number, it's not donating or accepting electrons, it's just serving as an atom that can be bonded to enable the others to form new compounds with their charges. So we've got the chlorine going from 0 to -1, so it's gaining 1 electron, and so because it's gaining 1 electron, we can say that it is being reduced, and because it's being reduced, we can say that it is the oxidizing agent. When we look at bromine, bromine is going from -1 to 0, so each bromine atom is losing 1 electron, because it's going from -1 to 0, and we're remembering that electrons have a negative charge. And so that means that because bromine is losing an electron, it is being oxidized, and hence it is the reducing agent. So bromine is essentially losing electrons and acting as a reducing agent by then donating those lost electrons to the chlorine so that the chlorine can be reduced. And then the chlorine is subsequently acting as an oxidizing agent to then gain those electrons which have been lost by the bromine. So next we're going to look at the double displacement reactions. So double displacement reactions are very similar to a single displacement reaction. However, instead of only one element being replaced, we've got two elements being replaced. So we've got AB plus CD makes AD plus CB. So we can see that there's this double switch over between these existing compounds and to then form these new compounds. So an example which we have here is we've got magnesium sulfate plus sodium bicarbonate makes magnesium bicarbonate and sodium sulfate. So in this particular reaction, we want to determine what our charges are that we're starting off with and what is changing, so we can determine what is being oxidized and what is being reduced. So when we look at magnesium, we look at magnesium sulfate to start off with, and we want to look into our rules. So our rules tell us that our oxygen is going to have a -2 charge, and each magnesium is going to have a +2 charge. But we also need to remember that we have 4 oxygens. So we can use rule 6 for oxygen and rule 7 for magnesium. However, we've got 4 oxygens, so we'll do -2 times by 4, and that gives us -8. -8 plus 2 from the magnesium is going to give us -6, which means that we want this to equal up to 0 as a whole, because it is needs to fit in with rule number 2, that it is a neutral compound, so it needs to have a charge of 0. So it's got -6, so in order to go from -8 plus 2 gives us -6, in order to get to 0, we need to then have a charge or an oxidation number of +6 for the sulfur. So then we can get -8 plus 6 plus 2, and that will give us 0. The next one we want to look at is our sodium bicarbonate. So we start off with, we can look at rule 3, and rule 3 is going to tell us that the sodium is going to be, we know it's a group 1 metal, so it's going to have a charge of +1 per sodium atom. So that's +2 overall because we've got 2 of them. Then we've got oxygen. So we can go into rule 6, which tells us we've got each oxygen is going to have its charge of -2. So we can do -2 times by 4. And so -2 times by 4 gives us -8. So -8 plus 2 gives us -6. And so now we need to fill in for the carbon. And so using rule number 2, we know that this entire compound does not have a charge on it, and it's neutral, so it's going to have an entire oxidation state of 0. So hence we need to get it to equal 0 with all those sums of the oxidation numbers. So this is -8, then +2 is going to give us -6, and then we've got 2 carbons. So we can't say that carbon is going to be +6 because there's 2 of them. We need to divide it between the 2 of them. So we do we need +6 in order to do that. So we do +6 divided by 2 is going to give us +3 per carbon atom. So if we've got 1 plus 1, +3 plus 3, -2 minus 2 minus 2 minus 2, that in total is going to give us 0. So now we need to look at what our products are to determine how these are changing. So if we look at our magnesium bicarbonate here, we can see that we've got magnesium. Following our rules, magnesium is going to be a +2 charge, oxygen is each going to be a -2 charge. So we've got -8 plus 2 gives us -6. Each carbon is going to be, each carbon here is going to be +3 because we've got 2 of them. So nothing's changed there. The magnesium is going from +2 to +2. Our oxygen is going from -2 to -2. And our carbon is going from +3 to +3. So nothing's changed in that context there. So we can completely ignore that for the moment, and we'll look onto our sodium sulfate. And so with our sodium sulfate, we first of all want to go to rule 3. And so rule 3 tells us that the sodium each sodium has a charge of +1, and so that exists to be the same as previously. Each oxygen has its charge of -2, so we've got -2 times by 4 gives us -8, plus 2 gives us -6, and then the sulfate is going to be +6. And so that also remains the same as well. And so we can see it appears that we don't actually have a redox reaction occurring within this reaction. However, if we're to break it down and we're to look in the data booklet, we've got these charges which happen for the ions. And so although each individual element on its own is not changing its redox charge, there's actual redox changes in the sulfate ion and the bicarbonate ion, but not within the individual atoms themselves. But you don't need to worry about that too much in terms of your exams and this syllabus, but I just thought it's useful to point it out in order to show you that although this can appear that it's not redox, it is still considered a redox type reaction and still can be a redox reaction. The next one we're going to look at is our combustion reactions. So combustion reactions, they basically always involve oxygen in the form of oxygen gas, so O2, and they're basically pretty much all of the time are going to be an exothermic reaction. And they're going to follow this typical rule where they need to have some sort of hydrocarbon, so something that involves hydrogen and carbon bonded together, then reacting with oxygen, and this occurs under heat and will form pretty much all the time is going to form carbon dioxide and water as its products. So when you see something where its only products are carbon dioxide and water, and there's oxygen as one of the reactants, you can typically then assume that you've got a combustion reaction. And so, although I did say that typically a combustion reaction is going to involve a chemical that is oxidized by oxygen, many other chemicals can burn in different environments, that being like nitrogen gas, chlorine gas, fluorine gas, but typically it's going to be oxygen, and that's the one which you look at throughout grade 12 and unit 3 and 4. But just here's some examples just to show that it does in fact occur under other circumstances, so don't be surprised if someone does mention a combustion reaction which burns in a different condition. So for example, we've got 2Ti plus N2 can make 2TiN, so that's a combustion reaction that doesn't have that typical appearance of carbon dioxide plus water. And then similarly, we've got like 3 magnesium plus nitrogen makes magnesium nitride. So these reactions, you wouldn't be expected to know that they're a combustion reaction. You would be told that they're a combustion reaction if you were given those type of reactions. However, ones like these here, up the top, where you've got your typical hydrocarbon reacting with oxygen and then producing carbon dioxide and water, you would obviously then be expected to know those are a combustion reaction because they're following that typical combustion reaction type pattern and reaction pathway. Our final reaction that we're going to look at is called a disproportionation reaction. And so in these types of reactions, you've got a single substance that is being both oxidized and reduced at the same time. And so this is going to be like this example here where we've got 2A makes A, and then you've got plus a number and A minus a number. So it's basically like one compound splitting into 2 compounds, one of which has been oxidized and one of which has then been reduced. So in this example up the top here, that's saying where N is your number of electrons which has been transferred. And so these reactions have some practical application, such as when you have hydrogen peroxide, which gets poured over a cut in terms of this, for sterilization, and this performs a decomposition reaction. And so we've got oxygen which is present in all parts of the equation, and it's being both oxidized and being reduced. And so this is why you keep hydrogen peroxide in a dark bottle, because otherwise it will just spontaneously decompose under the presence of light. So when we're looking at this, we can see we've got 2 hydrogen peroxide, or 2H2O2, makes 2H2O, 2 water, plus oxygen gas, or O2. And so when we're breaking this down into its oxidation and reduction, we can see that we can actually identify here that we have some exceptions to some of our rules. So we know that in our rules, hydrogen is going to have a +1 charge, and oxygen is going to have a -2 charge. But if we were to follow that rule in this particular circumstance, we would actually find that having hydrogen with a +1 charge and having oxygen with its -2 charge would not add up appropriately. So if we were to do hydrogen with a 2 plus 1 charge, we get plus 1 plus 1, so plus 1 by 2 will give us plus 2, and then we have got 2 oxygens, so we have minus 2 by 2, and so that will give us minus 4 plus 2, and that will give us minus 2 overall. And so we can't have minus 2 overall, because minus 2 overall would mean that this is not a neutral compound, and we do know that this is a neutral compound, so that would not be correct. So hence we've actually got to change the oxygen, because in peroxides, oxygen has a charge of minus 1. So in this circumstance, we can say we've got hydrogen is plus 2, each one being plus 1, and then the oxygen, each oxygen will be minus 1, so then overall 2 by minus 1 will give us minus 2, so we've got minus 2 plus 2 will give us 0 overall. Then when we look over here, we can see that hydrogen is going to stay the same at plus 1 because it is a spectator ion. But in water, we know that oxygen has its charge of minus 2, or its oxidation number of minus 2. So we can say that we've got minus 2 plus 2, that gives us 0 overall. So we can say that the hydrogen is acting as a spectator ion in this circumstance because it hasn't changed. It's just acting to be bonded to by the oxygen. But this oxygen atom has gone from a minus 1 charge to a minus 2 charge. And so because it's gone from a minus 1 charge to a minus 2 charge, we can say that it has actually then gained an electron per oxygen atom. Then when we look at O2 here, O2 follows rule 1, where we say that each oxygen atom is going to have a oxidation number of 0, and the entire compound is going to have an oxidation number of 0 because it's entirely made up of only one type of element. So in that case, we're going from minus 1 to 0, so that's a loss of 1 electron. So we can see that the hydrogen's not changing. The hydrogen is purely just acting as a spectator ion, but the oxygen is going in 2 different ways and is being both oxidized and reduced. So the oxygen here is going from minus 1 to minus 2, so it's being reduced, it's gaining an electron, whilst the oxygen to the oxygen gas is going from minus 1 to 0, which means it is going to then lose an electron per oxygen atom, and so hence it's being oxidized. So we've got half the oxygen in here acting as an oxidizing agent to then be reduced for the water, and half of it being acting as a reducing agent so it can then be oxidized for the oxygen gas. So now we're just going to look at a few examples of some common redox reactions which come up in day-to-day life. So our first example that we've got is cellular respiration. So cellular respiration being that we've got the formation of carbon dioxide and water from oxygen and glucose. And we've then also got the reaction of photosynthesis as well, which is following the same thing. We've got combustion, so that's what we briefly talked about before, but obviously we've got our hydrocarbon with oxygen, and then that's performing a complete combustion reaction, which then forms water and carbon dioxide, and also heat is an input but also an output from the reaction. As I sort of touched on before, photosynthesis, so we've got the sunlight, carbon dioxide going in, and that forms oxygen. The use of bleach is a redox reaction, which results in that color change. Corrosion, and so the ions which are losing electrons is actually what results in that breakdown of the metal, because so many electrons are lost that the metal actually just loses its integrity. Breathalyzers use a redox reaction. So now we're going to go on to balancing some redox reactions. And so when we balance a redox reaction, we actually want to split up the reaction into its half reactions. And so that just makes it easier for us to see the reduction reaction and the oxidation reaction. Then we can balance them and then combine the reactions back together to make it less clunky and just make it flow a lot better, and sort of simplify the process of balancing it. Balancing of these reactions doesn't work very well when you try to just balance them as they are as a whole reaction. So in order to split them up, we first will want to determine, well, what's being reduced. So we can see that we've got copper going from copper 2+ to copper solid. And so we can see copper solid has a charge of 0, whilst copper 2+ obviously has a charge of +1. So its oxidation number is going from +2 to 0, hence it is gaining 2 electrons, because we're remembering that electrons have a negative charge. So by gaining 2 electrons, it's going from +2 to 0. So we can say the gaining of electrons is reduction, and we're going from copper 2+ to copper solid. So we can write that as our reduction reaction. Next, we need to look at what our oxidation reaction is. So we can say that we've got aluminium, and our aluminium has its charge of 0, and so it's starting off with an oxidation number of 0. It's then forming aluminium 3+, which has a 3+ charge, and hence a 3+ oxidation number. So it's going from 0 to +3, which we can tell means that it is losing 3 electrons. So it's going to be oxidized because it's going from 0 to -3. We're taking away negative charge from it, so we're taking away 3 electrons, and that's going to give us a +3 charge. So we can say our oxidation reaction is aluminium makes aluminium 3+ plus those 3 electrons, because we need to have the charge balanced on both sides. So we can see that with our reduction reaction, we've got copper 2+ and then 2 electrons, so that on this side of the reaction, the net charge of this side of the reaction is equal to the net charge of this side of the reaction, because obviously we've got +2 and then -2. We can add those together, that's going to give us 0, and then this side 0, whilst on this side that's 0, and then we're going to have +3 and -3 gives us 0 on this side as well. So we can see our two reactions were not balanced in terms of their charge between them. So they were balanced, when we look back, we can see they're balanced for each side, but these two reactions are not balanced in terms of their transference of electrons. So if we're to consider our reduction, we've got a transference of 2 electrons. Whilst if we're to consider our oxidation, we've got a transference of 3 electrons. And so if we have a transference of that and they're in the same reaction, there's not an equal transference of electrons. So we need to make sure that it's balanced so that the amount of electrons that are being lost by the oxidation is the same as the amount of electrons that are being gained by the reduction. Because remembering that oxidation reduction with redox reactions is the sharing of electrons. So we need to find the lowest common multiple. So the lowest common multiple between 2 and 3 is going to be 6. So we need to multiply our reduction reaction by 3 and our oxidation reaction by 2. And so when we do that, we then get, we can then add up the reactions together. So we'll end up with 2 copper 2 plus, 3 copper 2 plus 6 electrons makes 3 copper solid, and then we'll end up with 2 aluminium solid makes 2 aluminium 3 plus 6 electrons. And so if we're to add those two reactions together to make an entire one reaction, we can put all the reactants on one side and all the products on the other side. And so when we're to do that, we get 6 electrons plus 2 aluminium solid plus 3 copper 2 plus, and that's going to make 2 aluminium 3 plus 3 copper solid plus 6 electrons. And so now we just want to check that we've balanced it correctly. So we can see we've got 6 electrons on each side, which we can actually cancel out because they're both on each side, so we don't need to specify that they're both there because there's no actual net change between each side. And then with our aluminium, we've got 2 aluminium on this side and we've got 2 aluminium on this side, so that is balanced. Then with our copper, we've got 3 copper on this side and 3 copper on this side, so that is balanced as well. So the final thing that we do is we just cancel out anything which has any double ups. So we've got 6 electrons on each side, so we can cancel those out because we just have a net change in electrons that we don't need to actually show there. So then we end up, as a final redox reaction, we end up with 2 aluminium solid plus 3 copper 2 plus makes 2 aluminium 3 plus 3 copper solid. So now I'm going to let you all have a turn to balance this yourselves. And so I'll give you 4 minutes to do this one on your own and see how you go, and then we'll go through the answer. So yeah, I'll give you 4 minutes for that. Okay, so now we'll go through the answer for this one here. So we've got aluminium solid plus hydrogen ions makes aluminium 3 plus hydrogen gas. So with this one, we first of all need to identify what is being oxidized and what is being reduced. So we've got aluminium, and it's going from 0 because we can see that it's solely just made up of one element, that being aluminium. So that's only that's rule 1, and so it's going to have its oxidation number of 0. Then it goes to a 3 plus charge, which is based on rule 2. So then we can see that if it's going from 0 to plus 3, remembering that electrons have a negative charge, it means that this one is gaining 3 electrons. So it's going from 0 to 3 plus, it's gaining 3 electrons. Then we can look at hydrogen, and so hydrogen, we can see here, the hydrogen atom has a +1 charge, and that's using part B of rule 2. And then we can see hydrogen gas has, using rule 1, has each hydrogen atom has a charge or an oxidation number of 0, and the entire thing is 0 as well. And that's because that's just solely made up of hydrogens. And so we can see hydrogen is going from +1 per hydrogen atom to 0 per hydrogen atom. So that means that, remembering that electrons have a negative charge again, this one is losing, hydrogen is losing 1 hydrogen atom. So 1 electron per hydrogen atom. So we can see that if aluminium is going to be losing 3 electrons, it's going to be being oxidized, whilst if the hydrogen is going to be gaining 1 electron per hydrogen, then it's going to be reduced. So we can write out, we've got 2H plus 2 electrons makes H2, and we've got aluminium plus aluminium 3 plus 3 electrons, and so that's our 2 separate equations. But remembering that we've got a transference of 2 electrons in the hydrogen reaction, which is our reduction reaction, and we've got a transference of 3 electrons in the oxygen reaction, which is oxidation. And so with our reduction reaction, we need to find, and our oxidation reaction, we need to find a lowest common multiple. And so that's going to be 6. So we need to times the reduction reaction by 3 and the oxidation reaction by 2. So that's going to give us 6H plus 6 electrons makes 3H2. And then over here for the oxidation, it's going to give us 2 aluminium plus 2 aluminium 3 plus 6 electrons. So we can put all of the reactants on one side and all of the products on the product side. And so we'll get 6 hydrogens, ions, plus 6 electrons, plus 2 aluminium is going to make 2 aluminium 3 plus 3 hydrogens, plus 6 electrons. And then we can cancel out any double ups that we have on both sides. So we can take out the 6 electrons on both sides, because that's just a net change of 6 electrons from both sides. So we don't need to show it. So then that gives us 2 aluminium plus 6 hydrogen ions makes 2 aluminium 3 plus 3 H2. So now we need to look at how we balance in acidic conditions. And so balancing in acidic conditions is the main condition type which you need to understand. For this, you'll see some places have how to balance in basic conditions, but for the sake of this syllabus and for Unit 3 and 4, you only need to know how to balance in the acidic conditions, not the basic conditions. So these are our main steps which we have for balancing in acidic conditions. So the first thing you need to do is write out the half reactions for each of the parts, so the oxidation and the reduction reactions. So same as you would always do for these. And then the next thing you need to do is balance for all atoms other than oxygen and hydrogen. So that's just your typical normal balancing. So the type of chemical reaction balancing you did in grade 10 and grade 11, just that type of balancing, and balance for all atoms other than oxygen and hydrogen. The next thing you want to do is balance for oxygen by adding water. And so using those oxygens in water in order to balance for oxygen. And then you need to balance for hydrogen ions by adding H+. And so it's really important that you always do step 3 before you do step 4, because if you do step 4 before you do step 3, you then aren't balanced for your hydrogen ions again, because water has the hydrogen in it. That would then disrupt that hydrogen balance. So you balance for oxygen first using water, then balance for hydrogen by using hydrogen ions. The next thing you need to do, which is step 5, is balance the charges by adding electrons to each side. So that's adding just a little E- symbol, and then however many you need, so whether it be 5 electrons or 4, and that's just putting it on whichever side requires more negative charge, so that each side has the same amount of charge on it. The final thing you want to do is make sure that the number of electrons are equal, and then once you've done that, you can add the half reactions together. So that's that process where you get all of the reactants, put them on one side, and then take all of the products and put them on one side. And so often you'll notice when you do that process of adding all the reactants on one side and adding all of the products on the other side, you might have 4 H2O plus 3 H2O plus whatever other compounds, or 5 hydrogen plus 7 hydrogen, and then all your other compounds. And so in that case, you can actually consolidate those. So if you have like 5 hydrogen plus 7 hydrogen on one side, you can actually add those together and just simplify it to being 12 hydrogen. The next thing you also need to do with that step 6 is taking away the electrons which you've added to both sides, so that they're balanced in that you don't have like a net change that's been displayed there. So if you have 5 hydrogen on one side, so 5 electrons on one side and 5 electrons on the other side, you can cancel those out. Same goes for if you've got, for example, 5 hydrogen or 5 water on the left hand side, and you've got like 4 water or 4 hydrogen on the right hand side, you could cancel those out as well. So if you've got 5 water on the reactant side and 4 water on the product side, you can take away the 4 water from the product side, take away 4 water from the reactant side, and that just leaves 1 water molecule on the reactant side and none on the product side. So it's just sort of simplifying out that reaction so that it's displayed more clearly. So we're going to do an example here. So we can see we've got dichromate ions plus chlorine ions makes chromium 3 plus chlorine gas. So our first step we need to do is separate them into their two half reactions, so an oxidation reaction and a reduction reaction. So our oxidation reaction being the chlorine 1 minus makes the chlorine gas, and our reduction reaction being the dichromate ions makes the chromium 3 plus. And so this is because we can see the chlorine is going from 1 minus to 0, because we're looking at part B of rule number 2, that's going to have the charge which is on it as its oxidation number. So that's -1. Then our chlorine is using rule number 1 because it's entirely made up of one element. So it's going to be having its charge of 0. And so hence its oxidation number for each chlorine atom and the entire molecule will be 0. So here we're going from -1 to 0 per chlorine atom. So that means that the chlorine is losing an electron, because we're remembering electrons are negatively charged. So we're going from a negative charge to a more positive charge. And so that means that we've then lost an electron per chlorine atom. Then with our reduction, this one's a little bit different in that we can see we don't have oxygen on the other side of the reaction. We've only got oxygen on the reactant side. So we know it's not oxygen which is participating in this particular reaction, but we do need to look at how the oxygen contributes to this. So we need to go through our rules for this one, in that we can see these dichromate ions have a charge of -2. And so this charge of -2 tells us that this entire molecule has an oxidation number of -2. Next, we know that rule number 7 is going to tell us that oxygen has its oxidation number of -2 per oxygen atom. But we've got 7 of them, so we need to do -2 times by 7, and that gives us -14. And so if we've got -14, but we need to get to -2, and we've got 2 chromium ions, we need to make up +12 out of our 2 chromium ions. And so +12 between 2 chromium ions, we do +12 divided by 2, and that's going to give us +6 per chromium ion. And so we can see our chromium ions are going from +6 to +3. And so if our chromium ions are going from +6 to +3, that means they're gaining 3 electrons. So they're becoming more negative because they've gained 3 electrons per chromium ion, and so hence that is a reduction. So we've got our oxidation reaction and our reduction reaction. So now we need to balance them. So we can see on this side of the reaction, we've got 1 chlorine, and this side we've got 2 chlorines. So we need to balance for those. So we're balancing for everything except oxygen and hydrogen. So we can balance for chlorine, and so that's done for the oxidation reaction. Then we can balance for, in our reduction reaction, we need to balance for the chromium, because we can't balance for the oxygen, because we need to balance for the chromium first. So we can see we've got 2 chromiums on this side, but only 1 chromium on this side. So we need to put 2 in front of this here. So now our reduction reaction is balanced for all elements other than oxygen and hydrogen. The next thing we need to do is balance for oxygen. So we don't need to do that for the oxidation reaction because the oxidation reaction has no oxygen in it. The reduction reaction, however, does have oxygen, and it has 7 oxygens on the reactant side, but none on the product side. So we need to put 7 water molecules on the product side of the reaction in order to get 7 oxygens on both sides of the reaction. Now we need to balance for hydrogen. So there's no hydrogens in the oxidation reaction, so we don't need to worry about that. However, in our reduction reaction, we didn't have any hydrogens on the reactant side of the equation, but we did have 14 hydrogens on the product side of the reaction. And so we need to get 14 on the reactant side, so both sides are balanced. So we can add 14 hydrogens to the reactant side of the reaction in the form of H+, or hydrogen ions. So we say we've got 14 H+ now on the reactant side. So we've got 14 hydrogens on both sides of the reaction. The next thing we need to do is balance for electrons. So we can see on the oxidation reaction, we've got 2 chlorine on this side of the reaction, and so that's 2 chlorine ions, so 2 Cl-. That means we have a 2- charge on the reactant side of the reaction, but on the product side, if we've only got Cl2, we've not got any charge on this side. So we've got a charge of 0 on this side and a charge of -2 on this side. So in order to balance, we need to add 2 electrons to the product side. So we've got -2 on this side and -2 on this side. Now for the reduction reaction, we can see that we've got 14 plus here, but then 14 plus -2 would give us 12 plus for the reactant side. And then on the product side, we can see each chromium ion has 3 plus, but we've got 2 of them, so the chromium ions have a 6 plus charge. And so we've got 6 plus on this side and 12 plus on this side. So in order to make those balanced and have the same charge on both sides, we need to put 6 electrons on the reactant side, so that we've got 12 minus 6 gives us +6 on the reactant side, and then we've got +6 on the product side. The next thing we need to do is make sure that the reactions are balanced in terms of their transference of electrons. So as we saw before, the oxidation has a transference of 2 electrons, whilst the reduction has a transference of 6 electrons. So in order to make that equal, we need to multiply our oxidation reaction by 3 so that it has the same transference of electrons as the reduction reaction. Because remembering that the oxidation is going to lose electrons to donate to the reduction reaction. So the reduction reaction is going to stay the same, whilst the oxidation reaction has now been multiplied by 3 to become 6 Cl- makes 3 Cl2 plus 6 electrons. So now we've got these fully balanced, we can then take all of the reactants and put them on the reactant side, and all of the products and put them on the product side. So we get 6 electrons plus 14 H plus dichromate ions plus 6 chlorine ions makes 2 chromium ions plus 7 H2O plus 3 chlorine makes 6 electrons. And then we can cancel out what's common on both sides. So we can know that's the 2 lots of 6 electrons. So we can take that off that side and that off that side. And that simplifies it down to our final reaction of 14H plus dichromate plus 6 chlorine ions makes 2 chromium ions plus 7 H2O plus 3 chlorine. So that is how you balance an acidic redox reaction. So now I'm just going to go over a few study tips before we finish up. So it's really important to note that the formula and data booklet is really important. So that's got all the important values and numbers that you need. And so it's really important that you utilize that, because there's no point remembering all that information. Electrons are really important. Just a recap, moles, they're just a unit of measurement, so don't get stressed out about them. And the final thing is just practice a lot, because you really need to practice continually and keep studying so you don't forget information. The next thing you need to do for learning this type of content, the best way to do this, there's quite a number of ways, and you just kind of got to try out which one works for you. But a few examples are you can do flashcards, you can draw out different processes, mind maps, active recall, teaching the information to someone else, doing recorded recall, doing practice questions and your homework under exam conditioned, so that's being timed and using the right calculator, mind maps and graphic organizers, doing regularly spaced retrieval, marking all your work, so there's no use doing the practice questions if you don't know if you're doing them correctly, creating a feedback or mistakes log so you can reflect on it and determine what you need to work on when it comes to your main revision time, keeping lots of variety in your notes, so adding it from multiple different sources, having tables, diagrams and dot points, using videos, sample explaining questions to people, traffic lighting your syllabus, so going through your syllabus and each learning intention, determining whether it's green light, orange light or red light, doing regular study so that you don't forget information, making yourself a cheat sheet of all the key points that you need, having a glossary of important words and definitions. Sometimes making a study group can be helpful if you work well with others, and finding your own creative ways to revise that work for you. So just a final summary of what we went over today, just to recap. So we talked about what are redox reactions and how do they apply to our lives. We talked about oxidation states, predicting and identifying redox reactions, and balancing redox reactions in our standard conditions and acidic conditions. And then just to recap, the basic conditions are not something you need to be worried about for year 11 and 12. And then finally, we just finish off with a few study tips. And yeah, so that's everything for today. Thank you for watching, everyone, and good luck.